Hey guys, this video is going to explain to you a few things about this worksheet that you're supposed to be doing in class. You shouldn't watch this video unless you've already tried all the questions on it. Or maybe you want to go through it piece by piece and do a problem, check and see if you understand it. Or you also have the answer key, which is posted in the Google Drive that you can look at if you're like, I don't have time for a video. Okay, so that's fair. You can go and look at that, and if you understand the work and the explanations that I've written down, then you don't even need to watch this video. But if those aren't enough and you need some good old-fashioned explaining, then this should help you. All right, so the first question says we have a car going down a hill. No engineer would actually build a hill like this. This is terrible, but whatever. Suppose that this is exactly what things were shaped like. And it says the radius of curvature of the hill is 8 meters. All right, well, where you need to begin with this, just like with any forces problem, is you draw a force diagram. You have to indicate all of the forces that are acting on the car, both at the bottom and at the top, because your different parts of the question are going to deal with when it's at the bottom, others deal with when it's at the top. And yeah, this radius of curvature is also 8. Okay, so when it's at the bottom, I mean, of course gravity acts on it. Gravity will act on it anywhere. So never leave out gravity. All right, the next thing that has to be acting on it for sure is the normal force, because it's on the ground and it's not like falling, right? It's clearly on a surface, right? Later on we'll talk about what if the car becomes airborne and then it's not touching the ground anymore, all right? But if it's on the ground down here, there's got to be some normal force holding it up, since it's not digging into the concrete. All right, now the thing that is missing here is this is what it would look like if it was just sitting at the bottom. In all of these various diagrams here, we have to show in the centrifugal force. So the qualities of the centrifugal force are that it is mv squared over r for the formula, and therefore something has to be moving in order for it to experience a centrifugal force, right? V has to not be 0, all right? Which is why this would be correct for it just sitting there. The second quality is that it goes out from the circle. So if this is the circular arc that the car is moving in, right? There's the circle. Out from the circle would be down. And therefore, my sum of vertical forces equation would look like N minus mg minus Fc equals 0. All right, so the centrifugal force then always goes out from the circle. And now I can plug in my numbers and things. All right, so I know the mass of the car. I am told the speed of the car, and so the normal force will equal mg plus Fc, which is mv squared over r, as we set up there. And apparently when you get those numbers and plug them in, you get 27,800 newtons, which is a lot of newtons, but not necessarily that surprising, because after all, it is a car. Cars are big, and it does say that it's moving at 12 meters per second, which is decently fast, around, honestly, a really pretty tight circle. Like, this would be an uncomfortable ride. All right, now, for the one at the top, same idea. You have, well, normal force, the ground is holding it up. Gravity's pushing it down. All right, the difference, though, is if it's going this way, right, our circle is like that. Out from the circle would be up. So therefore, when we do the sum of the forces for that position, we will have, or sum of the vertical forces, N minus mg plus Fc, since the centrifugal force is in the same direction as the normal force. So therefore, the normal force will be mg minus Fc is mv squared over r. All right, so now when I plug in those numbers, it says it's moving at 8 meters per second at the top, so it's slowed down a little bit. I'm going to get that it's 1,800 newtons, which is substantially different. All right, but fine, that's what we have. All right, now part C is leading us into something which is really important about circular motion, which is very frequently there's either a minimum speed or a maximum speed that something has to have to stay moving in a circular path. So there's not really such a thing as a maximum or a minimum speed down here unless the limit is you pop your tires, okay? But up here, I mean, you guys have probably gone over a big hill before and felt a low lurch in your stomach, right? And that's the contents of your stomach momentarily being airborne, since you are essentially approaching free fall because you took the top of that hill too quickly. When you get to part C of this question, and they have you plug in that faster speed, since it's, mg minus mv squared over r, you get this surprising result at a faster speed, which is that the normal force comes out to negative 325 newtons. What would a negative force be? You can't have a negative force. You can have a force in a negative direction. And actually that's what that ends up telling you, is that if you are going, in part C it says 9 meters per second. If you were going just 1 meter per second faster when you crest that hill, the centrifugal force is larger than the gravitational force. And therefore, in order for you to stay on the road would have to somehow be pulling you downwards. That doesn't make any sense. That's not, a road can't do that, okay? You may have been on a roller coaster before where you felt like you were being flung outwards when you reached the top. And in that kind of a case, a roller coaster has rails that have a wheel that fits inside of it. So the rails can push you down if you would tend to fly up off the track, or they can hold you up if it's a slower speed, more normal situation. Okay, but clearly we can't go as fast as we like here, because if the normal force goes negative, that means that we would only maintain contact with the ground if the ground could somehow pull the car downwards. All right, so therefore there is a maximum speed. The normal force can at most, maybe I'm saying that backwards, can at the smallest possible value be 0. All right, so whatever, it can be any large number you like. The ground's not going to be smashed by your car, but there is a sort of, I guess a minimum value would be the right way to say that, right, of 0. It can't go negative, because you get a negative number, you are very airborne. So therefore, there's a maximum speed that you can solve for by saying that the normal force is 0. If you would go airborne or otherwise lose contact with the ground, then at that point that means the ground is no longer holding you up, and so therefore the normal force would be 0. So therefore, when you get to part D and it asks you what is the normal force when the car moves at its maximum speed over the top of the hill, we say 0, because at the maximum speed that you could go without becoming airborne and losing contact with the ground, the normal force would have to be 0, because it's just barely not holding you up. All right, now if you want to know what the actual speed is, that is its maximum speed without becoming airborne, we can take our formula that we got right here, I guess this equation right here for the sum of the forces, and this is part E now, and say at the maximum speed, the normal force will be 0. In other words, the only thing holding you down to the ground is gravity. guess maybe the other way around. The only thing that's keeping you moving in a circle is gravity, since the normal force is no longer helping you stay circular. All right, so that means that if I move the mg over or the fc over, however I do this, I'm going to get mg equals fc. So that's mg equals mv squared over r. And I can solve then for the maximum speed. Cancel out the mass, and the maximum speed that you can have is root gr. Right? Multiply both sides by r, so you'll get gr. And then it's a squared, so we're going to take a square root and get this result, which in this case for the car works out to be 8.85 meters per second. Obviously, if we had a different shape of road, it wasn't a very poorly engineered hill like this, radius of curvature of, let's say, 50 meters, it would be a lot harder to get airborne. All right, but if you do have a steep hill like this, it's very easy to become airborne because this really isn't all that fast. I want to say that's something like maybe 20 miles per hour, maybe 30. Okay. All right. So this formula of root gr is going to come up a lot whenever we ask about either minimum speed or maximum speed when something is moving in a circle. And usually the assumption that you make in those kinds of problems is that the normal force is going to be 0, or if it's a question with something, say, spinning on a string, that the tension force is equal to 0. All right, on the other side of the paper, you have a related question, right, where they give you a loop-the-loop kind of a problem. So there's a little block going down. If you look at it when it's up here, it's got gravity, normal force. Now, which way would normal force go? Correct answer is not up. Normal force does not push the block up. It's moving around inside of the track. So the normal force would be down. All right, and the centrifugal force would be out of the circle, which in this case would be up. All right, so the calculations end up being a little bit different. For the car, there's a maximum speed you can go without becoming airborne and therefore leaving a circular path and turning into a parabola. In this case, there's a minimum speed instead of a maximum, where if it's going any slower than that when it gets to the top, it will just fall off the track, right? It will not go and complete the loop-de-loop, it will go, whoa, right? Which, if you've played around with Hot Wheels, is something that I'm sure you've experienced before, when you have something that just isn't going quite fast enough when it goes around the loop-de-loop and it just falls, and probably as a child you were disappointed or just wanted it to work better. All right, and so the key would be, of course, making it go faster when it gets there, because there's a minimum speed that it must have. All right, the calculations for that go kind of similar to what we did here. All right, the sum of forces equation, however, has the normal force in the other direction. So some things are different. You have that instead. Okay, I'm going to skip over the rest of that one, though, and look at the last problem with the spinny ride. So, here we go. The spinny rides are in real life, they're even more fun for physicists because the force equations and the force diagram are so weird. Okay, the normal force goes sideways. Since you're spinning in a horizontal circle, the centrifugal force goes out of the circle to the right. And then you have gravity pushing you down and friction holding you up. Just about out of time there, so there's the work in another form. Hope that helps.